Today we're going to be taking a look at critical points of a function in two variables. So for the demonstration today, we've selected the function z is equal to cos x squared plus sine y squared. Yeah. So for any of these points, or any of these sort of minimal things or maximal, we could just go ahead to simplify things and drop a plane down into it, so that we can sort of illustrate where these minimums are. So here I've put a yellow plane down at a minimum value of y in the y direction. So just kind of looking at it head on. Now what that ends up doing is kind of reducing the function down to just a function of x. And if we trim it a little bit more, we're left with just sort of a ribbon. It really shows you, here's the cosine of x squared. And so we know that where we've trimmed it on the y-axis was actually a minimum. And so now here we have the x, and it has its own maxima and minima locally here in this little section that we've got. And so we can sort of further break this up, and maybe we want to look at a minimum value. So this is a local minimum for the surface, which here's the back side of it, kind of what's left over. So when we have this intersection of, we've got a minimum in the y, minimum in the x, if we look at the actual surface itself, we can go ahead and pin that point, and we know that's going to be a local minimum. And so similarly, you could do this over and over again. There's a whole bunch of them. There's each kind occurs in this particular function over this range. So here's a second one that I just put in. It's over on the back side. A bit more of an interesting point. This is a saddle point. So in the y direction it's a maximum, but in the x it's a minimum. I wind up with 21 local minima and maxima over this small section of surface. So between negative pi and pi, and then pi by 2 and negative pi by 2 in the x and y respectively. So just continuing on with all the different planes, this is kind of what it looks like, totally sectioned off. So each intersection is one of the critical points of this surface. So the other fellows are going to break it down a little bit and talk about the actual numbers, where these fall. But yeah, this is it for a bit of an intro to what we're looking at. Thanks.
Hello everyone. The function we are going to plot is cos x squared plus sine y squared, which is a function of two variables that produces a 3D surface. To plot this function in SageMath, we'll be using the plot3d function, which takes the function and two ranges of x and y values as arguments. Now I will take us to the SageMath screen. Before plotting, I have defined some variables, x, y, and z to be exact, that we will be using further in our codes. And now let's define the function itself, that is cos x squared plus sine y squared, which we are going to plot. To create the plot, we'll use the plot3d function. Here is the code that I wrote. As mentioned, I have given the ranges of x and y values, where x will be between minus pi and pi, and y will be between minus pi by 2 and pi by 2. Now let's display the plot. As we can see, the code has generated a 3D plot of the function cos x squared plus sine y squared with the ranges that we have specified in the code. Thank you.
Thank you very much for the introduction, John. Now we'll be looking at the critical points for this function, but I will be doing only in terms of x. So we have the function given as cosine x squared plus sine of y squared, and the range of x is given as negative pi to plus pi. So starting the partial derivative in terms of x, we have cosine x squared plus sine y squared, and the sine of y squared goes to 0 because there's no x there. So cosine x squared, first the outside, and then the inside, we'll derive the inside. Just for the outside derivative, we have negative sine x squared, and now the derivative of the inside, x squared, that's just 2x. So we have final as negative 2x times sine x squared. Now setting this partial derivative to 0, we can find the values for x, which is sine of x squared equals 0, which is only true for all values of x, which is root of n times pi or negative root n times pi, which is true for all integers n. Now given the range of x, which is negative pi to plus pi, we have the following values: x is equal to 0, root pi, root 2 pi, root 3 pi and the negatives of them. That is it from me. Thank you very much. Over to you, Hakeem.
Thank you, Amrinda, for that very concise and nice explanation. Now we'll see what happens when you derive this function in terms of y. Again, keeping the range between negative pi over 2 and pi over 2. So we have this function again. We take del of the function times del y for both sides, so we keep x or any other variable as a constant. So you derive cosine x squared, that is minus x squared, but then you derive using the chain rule, you multiply by the derivative of the inside function, the derivative of a constant is 0, so therefore that gets eliminated immediately. Derivative of sine y squared is cosine y squared times the derivative of the inside function, the derivative of y squared is 2y. So we set this up to 0, keeping in mind the range, and 1 should immediately pop out at you as a critical point because anything times 0 is 0, so if y is equal to 0 on that 2y, it doesn't matter what 2 is, it doesn't matter what cosine y squared is, it will always be 0, again, as long as you can put in 0, and there's no asymptote or anything preventing that, so that is perfectly permissible. So to find the rest, we divide both sides by 2y, again, assuming y is not equal to 0, since you can't divide by 0, but we already have that as a critical point, so we're just going to ignore that for now. So I take the inverse of these functions, so the inverse of cosine is arc cosine, and thinking back to the graph, cosine starts at 1 and then goes down to 0, and obviously cosine is 0 at an infinite number of angles, but arc cosine limits the amount of angles you can pick, so it is going to be pi over 2 as our angle where it equals 0, so that's what we have, and then we have to take, again, the inverse, but this time we have the squared, and to take the inverse of the squared, we take the square root, and remember, when you're taking the square root of something, you have to keep in mind both roots, the positive and the negative, so we take the square root of pi over 2, we get plus or minus square root of pi over 2. So there you have it, folks. This is the critical points. When you derive for y, you have negative square root of pi over 2, 0, and square root of pi over 2. Thanks for watching.
Hello, my name is Nicholas, and my role for this project was to classify each of the 21 critical points using the second derivative test of this function here, cosine x squared plus sine y squared. This is the second partial derivative test that I'm using. I'm not going to explain it, but so what I did first was, in order to avoid doing these calculations manually, I made this function that essentially just does the second derivative test for me if you give it a function at 2 points. This is confirmation that it works, and then I made these two lists, the list of the critical points in the x-axis and the list of the critical points in the y-axis. There's 7 total x, 3 total y, and if you just combine those in all the possible ways that you can do it, you get 7 times 3 is 21. I then went through, I iterated through all the points and basically added to a list the point itself, the value of the partial derivative with respect to x at the point, and the value of the second derivative test at the point. And then, obviously it looks kind of disgusting and you can't make anything out of it, but in order to make things more clear, I just manually went through and separated the points into their classifications based on the second derivative test. So the saddle point...
My name is Chanel, and my role is the conclusion of the project. Our goal was to find the critical points of a two-variable function. We use the cosine x squared plus sine y squared function. To find the determinants, we can use fxx or fyy or fxy or fyx, but we use the first derivatives of x and y, and we found there are 21 critical points, and this is the cosine x squared curve, which shows the 7 critical points in the x-axis, and this shows the 3 critical points on the y-axis, and there is a subtle point in the middle where there is a maximum on the x-axis and a minimum on the y-axis. And when you insert planes to find the intersections, you can clearly identify the 21 critical points that Nicholas calculated, and using the graph of John you can confirm it. Thank you.